In this portion of the class, we're working on analyzing recursive algorithms. We've already talked about the process of taking a recursive algorithm and developing a recurrence relation that describes how many steps that algorithm will perform. In this video, we're going to be focusing on solving those recurrence relations. And solving recurrence relations is a big topic. It can be challenging. In fact, it's entirely possible to be faced with a recurrence relation that doesn't have a closed form solution at all. But for the kinds of recurrences that will come up when we're doing algorithm analysis, we often can solve them. There are different ways to go about it. And in this video, we're going to focus on the method of backward substitution. And the algorithm that we're going to practice on is binary search. So this is a nice example for us because it's a very practical, important algorithm. It's an algorithm that we've already put some effort into thinking about its performance from a non-recursive perspective. So we sort of have a sense for what the answer should be when we get done. So as a reminder of how binary search works, we are faced with some array, and we're looking for a particular element, and this is a sorted array. All of the elements are in order. So the logic is that I'm going to look at the midpoint of the array. That's calculated here. I'm going to check to see if the value that I'm looking for is at that midpoint. And if it's not, I've learned something important. So let's say that the element that I'm looking for is greater than what I was searching for. Well, I've excluded the position where I checked, and I've excluded everything to the left. And I know that the element has to be over here somewhere. So why is this a nicely recursively structured problem? Because once I've determined that the element isn't over here, I know it must be in this portion of the array. And now the way of searching in that portion of the array is just going to be to perform a binary search. And how do you do a binary search? Well, I'll pick the midpoint of that region of the array. I'll check to see if the element that I'm looking for is there. If not, in the worst case, it's going to be over on the right somewhere. I've excluded that, and now I'm going to perform a binary search on this portion of the array. And the base case is going to occur when I get down to the point where there's no elements left to search for, or I've found the thing that I'm searching for. So that's the recursive structure of binary search. So our first goal is to somehow figure out what the base case is and somehow figure out how to describe the amount of work that this algorithm does as a recurrence. And the first question that arises is, what's our n here? How are we describing, if I look at this code, what is the size of the input to the algorithm? Some of the examples that we've seen earlier, n was some number that was explicitly passed along to the recursive call, and that was capturing how big the input size was in some direct way. That's not really the case here. So start isn't the size of the array, end isn't the size of the array. The way to think of it is that the size of the array, or the size of the input, is the size of the region of the array that we've been asked to search in. So initially, that's going to be the entire array. And then as we make subsequent recursive calls, that size of the array is going to shrink. And in general, it's going to be something like end minus start. That isn't quite right, because when start and end are the same, this would suggest that the size is 0. But in fact, in that case, there is still one element that we're looking for. So this is the way we would express, this is the way we would calculate the input size from these arguments. So that's the way we're going to think about the input size. That's the way we're going to think about n. It's the size of the piece of the array that we've been asked to deal with. So we can fill in these values here. So the base case, well, let's call the base case an array of size 1, or a subarray of size 1. And at that point, what we're counting is the number of array elements we're going to look at, the number of array comparisons, and that's going to be 1. We just have to look at that last element, and either we've found the thing or we haven't. And how about the recursive case? Well, actually, let's express this using W to make it very clear that what we're doing is a worst case analysis, right? In the best case, it's always one step. We just happen to find the thing that we're looking for immediately. So we'll describe this as the worst case. And in the worst case, well, we have to make a comparison in order to decide which way to go. And then we have to recursively analyze the remaining portion of the array, and that's going to be n over 2. We've cut the size of the array in half. If we wanted to be very precise, we could probably put a floor here. It's fine to leave that out if all we're interested in is the big theta answer, or it's not uncommon to say something like, well, as long as n is exactly a power of 2, this is going to be an exact answer. And that's the kind of analysis that we're going to be doing here. Leaving that floor in would make analysis basically impossible to get a closed form solution, or very, very difficult to get a closed form solution. So that's the recurrence that we're dealing with. And you might be thinking, great, we're done. But of course, what we really want is the closed form answer. And we needn't have done come up with a recurrence or solve that recurrence at all to come up with that closed form answer. In fact, this is something we talked about earlier in the semester. And we thought it through just by working through some examples, building up a table of how many steps have happened in the worst case for particular input sizes. And what we came up with was that, in fact, binary search requires log base 2 of n plus 1 steps in the worst case, or exactly floor log base 2 of n steps. But how could we use this recursion? So this is the closed form. This is the answer we want in the end. But we can use this to come up with any one of those values. So for example, let's say we want W of 8. Well, I can find W of 8 through the power of backward substitution. It's not the base case. So I'm going to plug in 8 for n and see what I get. And I'm going to get 1 plus W of 4. Great. Well, that's not the answer, but I can continue substituting into my recurrence until I get down to the base case. Well, so this whole thing is equal to 1 plus, well, what's W of 4? I can plug 4 in for n, and I get 1 plus W of 2. So this becomes 1 plus W of 2, and then I can do that again. It becomes 1 plus 1 plus 1 plus W of 1. This doesn't require any more substitutions. That's the base case. So I know that that's equal to 1. So my final answer is 1 plus 1 plus 1 plus 1 equals 4. Log base 2 of n plus 1. And it required 3 substitutions to make that happen. So the way we're going to, so that's great, right? And we can use that for any value of n. So if n is 64, if n is 128, we can start plugging in and continue to substitute till we get to the base case. But of course, that's not what we want, right? What we want is to know this closed form solution, to find this closed form solution so that I can just plug in my n and get the answer directly. And the way we're going to get that closed form solution is basically to follow this method of backward substitution, but to generalize it, to say, I'm not going to be working with 8, I'm going to be working with n. And so let's just go through that process. Okay. I'm going to write the recurrence that I want to solve up here. It's W of 1 equals 1, and W of x equals 1 plus W of x over 2. I'm writing an x here just because I'm going to be using n to represent my input size as I'm working through, and it can be a little confusing to substitute an n in for an n. Maybe it'll be slightly less confusing to substitute an n in for an x. Okay, so I want to know, in the end, what is W of n? And I'm going to figure this out by repeatedly substituting into my recurrence over here. And I'm going to keep track of how many times I've done this substitution, and I'm going to call that I. So this will be my first substitution. And I'm going to put some scratch area over here, which I'm going to use to figure out what those substitutions work out to. This one's pretty straightforward. If I plug in n here for x, then I'm going to get 1 plus w, and then n goes in for this x, so it's n over 2. Great. But now I need to figure out what this works out to. And that's where I'm going to use my scratch area over here. I'm going to say w of n over 2 equals what? Well, I'm going to take this n over 2. I'm going to plug it into my recurrence for x. So every place where there was an x, there will be an n over 2. So I'm going to get 1 plus w n over 2 over 2. Great. That's a sort of funny way of writing that. We can simplify that, do a little bit of algebra, and call that 1 plus w n over 4. So now I know what w n over 2 is, and I can replace this w n over 2 with that, and that is exactly what I'll do. So this w n over 2 is replaced with this thing, and that is now what I've worked up to. Great, and that represented 2 substitutions. Let's do one more substitution. Oh, and one thing to point out, you may be wondering why I didn't just add this one and this one together to get a 2. What's often going to happen when we're solving these recurrences is that we'll end up seeing a summation sort of forming over here on the left. And if we act too aggressively to add those things up, then we can lose the structure of that summation. So I'm going to stay out of the habit of sort of collapsing these terms over here. All right, let's do another substitution. I want to know now, well, what's that work out to? And again, I'll use my scratch area over here. And thanks to Professor Bowers for showing me this nice way of setting up these problems. Wn over 4, well, what's that equal? I'm going to take that n over 4, plug it into my recurrence. So every place I have an x, I get an n over 4. 1 plus w n over 4 over 2. And that can be rewritten a little bit more nicely as 1 plus w n over 8. And that is going to be what I substitute in here, right? We know that w of n over 4 is equal to 1 plus w of n over 8. So I can replace this w of n over 4 with that. If I will do so, I get 1 plus 1 plus 1 plus w n over 8. Great. You may be getting worried at this point. You may be saying, where are we making progress? How is this progress? I could keep doing this substitution process forever, right? The next row you can anticipate would be 1 plus 1 plus 1 plus 1 plus wn over 16, and so on. And you're right. So the idea at this point, and usually it's going to take about 3 substitutions before we're in a position to do this, is to generalize this for an arbitrary value of I, so that I don't have to make any more substitutions. I can just figure out what this will look like after any number of substitutions. So what's this going to look like in general? Well, when I was 1, it was 1 plus w of n over 2. When I was 2, it was 2 plus w of n over 4. When I was 3, it was 3 plus w of n over 8. So it looks like it's I, whatever I was, is the sum of the things on the left over here, plus w of n over something, and that went from 2, which is in fact 2 to the 1, to 4, which is 2 to the 2, to 8, which is 2 to the 3. So it looks like in general that's 2 to the I. So this is what my this is what I get when I start with W of n, and then I start making recurrences after I recurrences. And when do I stop, right? So when we were looking at the case of W of 8, I kept doing that until I got to the point where I had a 1 in my W here, right? When I hit the base case. And that's exactly what we want to do here, right? How many times do I want to substitute? Well, it depends on n. If it's a bigger n, it's going to take more substitutions, but I can actually calculate that. I can find, by doing a little bit of algebra, how many substitutions it's going to take to get back to my base case. And that algebra is just to say n over 2 to the I equals, right? So this is what I'm getting for after any number of substitutions. And when I get to stop is when that is equal to this, when that is equal to the size of the base case, in this case, 1. Well, so what can I do here? I can multiply both sides by 2 to the I, so I get n equals 2 to the I. Now I want to get rid of this. I want to get this I pulled out, so I'm just going to take the log of both sides. So I get log base 2 of n equals I. And this is then telling me for any value of n, it takes exactly log base 2 of n substitutions before I hit the base case. And if I want to know what the actual closed form answer then is, all I have to do is take that log base 2 of n and plug it in for I. So my final answer is W of n equals log base 2 of n plus W of n over 2 to the log base 2 of n. And of course, 2 to the log base 2 of n is just n, and n over n is just 1. And that's the base case. And we shouldn't be surprised because that's how we picked log base 2 of n. So that becomes log base 2 of n plus 1, which was the answer that we expected going in. So in this case, we knew what we expected the answer to be. In general, we don't, right? In general, we wouldn't be going through the trouble of solving this recurrence if we already knew what the closed form solution was. And it's easy to make a mistake. So we wouldn't stop at this point, or we wouldn't go home. We wouldn't publish this as our final answer. We would want to sanity check it to see if it actually works out. So what's W1? I can figure that out by using my recurrence, and I know that it's exactly 1. I can also figure it out by using my closed form solution here. So W of 1 equals log base 2 of 1 plus 1. 2 to the 0 equals 1, so this is 0, so that's 1. Okay, how about W of 2? I can plug that into my recurrence over here, and I get 1 plus W of 1 equals 2. And then I can plug it into my closed form solution here. W2 equals log base 2 of 2 plus 1. And log base 2 of 2 is 1. So that's 1 plus 1, 2. And of course, I could do that. I'd probably want to do that for a couple more, or at least one more to make sure that it looks like I've got the right answer. But in this case, it seems to be working out. Okay, let's do one more example. And here we'll pick an algorithm where we don't know what the answer is going in. So this says that we should be counting this comparison as our basic operation. And let's take a quick look at the structure of this algorithm. An array is passed in. Once again, we're passing in a start and end index, indicating the region of the array that we're still processing. When start is greater than or equal to end, we're done. So when we're down to a size of 1, that looks like. And so that looks like the base case. Otherwise, we check to see if the values at the first position are equal to the value at the first position is equal to the value at the last position. If it is, we return false. And we don't get into the recursive case, so we'll be doing another worst case analysis here. We'll assume that that never happens. So then we get to the recursive case, and that involves 2 recursive calls to this algorithm, and each of which is picking a piece of the array to look at. So how's that look? If my array looks like this, right? My initial start and end are here. And it looks like my first recursive call is going to process everything from start to end minus 1. So it's going to process all of this, but not this last element. And my second recursive call is going to process everything from start plus 1 to end, all of this, but not this element. So if my original array size was n, the original region of the array that I was looking at is n, it looks like I've got 2 n minus 1 pieces that the recursive calls will each process. So we can turn this into a recurrence. What is the base case? The base case is when we're down to an array size of 1, and it looks like there are no comparisons in that case. So I would say W of 1 equals 0. And what's the recursive case? The recursive case is, the worst recursive case is we make this comparison, it doesn't succeed, so we make these 2 recursive calls. And at that point, right, once we've made that comparison, well, we've done one comparison, and then we're going to make these 2 recursive calls, each of which is going to be of size n minus 1. So that's the recurrence that we want to solve. And let's just work through that same process. We'll go back to the drawing board to work it out. So our recurrence was W of 1. Let's go. Recurrence was W of 1 equals 0. W of x, again, we'll use x here, equals 1 plus W of x minus 2 W of x minus 1. All right. Let's go through the same process again. So we'll start with W of n. And what does that work out to? Well, I'm going to take n, and I'm going to plug it in for x, and I'll get 1 plus 2 W of n minus 1. Great, and that's what I get after one substitution. Okay, now this I need to replace. I need to substitute in to do that. Once again, I'll make my scratch area over here. And I need to figure out what is W of n minus 1. Well, I'm going to take n minus 1. I'm going to plug it in for x over here. And I'll get 1 plus 2 W n minus 1 is going to go in for that x. So I'll get n minus 1 minus 1. That can be tidied up a little bit to be 1 plus 2 W n minus 2. Great. So W of n minus 1 is equal to this. This W of n minus 1 is equal to this. So I'm just going to replace this W of n minus 1 with this thing. And what I'll end up with is 1 plus 2, right? Gotta keep that 2 there, times this whole thing. 1 plus 2 W n minus 2. Great. So I said earlier, I don't want to collapse all of this, but I am going to distribute the 2 at least. So I'm going to make that 1 plus, so that's 2 times 1, so we'll call that 2. 2 times 2 is 4, w of n minus 2. And all of this was the second substitution. And like I said before, it's generally going to take at least 3. So now we have to substitute away this guy. And what's he going to work out to? N minus 2. Take n minus 2, plug it in for x over here. I'm going to get 1 plus 2 w n minus 3 in this case. So that's what this will turn into. So let's just plug it back in. 1 plus 2 plus 4 times this thing, right? That's what wn minus 2 is equal to. 1 plus 2 wn minus 3. Fantastic. And then again, I'll distribute the 4. So I'm going to end up with 1 plus 2 plus 4 plus 8 w n minus 3. And it might be helpful, right? We can see, hopefully you can see that these are powers of 2. This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So it might be helpful to just rewrite it that way. Incidentally, all of this is our third substitution. So 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 to the third w n minus 3. Great. Now the next step is to generalize this. And this one is significantly more complicated than the last one we saw. And we'll often have these two pieces, right? We'll have the summation over on the left that doesn't include our recurrence. And then we'll have the recursive part over on the right. So this looks like the summation of 2 to the 0 plus 2 to the 1 plus 2 to the 2. This was at the third substitution, so it looks like we're stopping one short of whatever substitution we're on. So I'm going to write this as sum of j. I'm using j here because we've already used I, even though it's common to use I as our variable in this sigma notation. So j equals 0 all the way up to, not to I, because I was 3, but we stopped at 2. So I minus 1 2 to the j. Great. And here, well, this looks like it's 2 to the I times w of n minus I. All right. So this is the general form. For any value of I, we can plug in I here and we'll get what we would have gotten by continuing to make substitutions. We don't like summations, right? This is a summation that we know the answer to, though, fortunately. We've seen it earlier in the semester. So I equals 0 to n equals 2 to the n plus 1 minus 1. So you can just take my word for it. Oops, sorry, of 2 to the I. So I can get the closed form of this summation in terms of I by plugging I minus 1 in up here. So that would give me 2 to the I minus 1 plus 1 minus 1 here equals 2 to the I minus 1. So that's what this works out to. We still don't know what I is, but we can get rid of the summation. So that's equal to 2 to the I minus 1, and we've still got the 2 to the I w of n minus I. Okay, we're getting there. Now all we need to do is figure out how many of these substitutions are required for any particular value of n to get to the base case. And again, that just involves figuring out when this thing is going to be equal to the base case. So that's just solving n minus I equals 1, because that's the size of my base case here. Great. I can subtract I from both sides, or add I to both sides, I'd get n equals I plus 1, and then I can subtract 1 from both sides. I'll get I equals n minus 1. So it takes n minus 1 substitutions to get down to the base case. Great. So now all I have to do to finish is to take this, plug it in for I here, and that'll give me my closed form answer. So W of n equals 2 to the n minus 1 plus. I could go through the bother of substituting this n minus 1 in here, but I can also just notice that it's 0, right? I know that this is going to work out to 0. So this is my final answer. I think it's my final answer. I may have made a mistake. Gosh, look at all of this. It would be easy to make a mistake. So I wouldn't close the door on this until I had checked a couple of values of n against my actual recurrence. So W of 1, plug that into the recurrence, I would get 0. W of 1, plug that into my closed form solution, it's going to be 2 to the 1 minus 1 minus 1. So that's 2 to the 0 minus 1. 2 to the 0 is 1. So that's 0. Great. W of 2, plug that into my recurrence. I'm going to get 1 plus 2 times 0. It's going to be 1. When I plug it into my closed form answer here, I'm going to get 2 to the 2 minus 1 minus 1. So that's 2 to the 1 minus 1. And that's going to be equal to 1. So this is working out. Looks like I got the right answer.